Okay, so at this stage, let's start with a quick recap of the things that we've learned about rate of change so far. Okay. So talking about rate of change, first we had seen rate of change with a common example of the application of that concept, that speed equals to the rate of change of distance with respect to time. Of course, you can also say that velocity equals the rate of change of displacement with respect to time. But velocity and displacement being vector quantities, okay, whereas speed and distance being scalar quantities. I want to keep the definition right now simple. So we are relating to scalar quantities, that is quantities which have only magnitude and no direction, and that is speed and distance, and this is how they are related. Okay. However, we talk about two types of speed. We talk about average speed. So this is defined for an interval of time. Say t equal to t1 to t2. So that is defined, as we saw, as the total distance divided by the time interval. So that is S2 minus S1 divided by T2 minus T1. Okay, we have done all this previously, but I'm just taking a recap of this concept. So when we again understand differentiation today, you will see the significance of these from the point of view of calculus. Okay. The second type of speed that we talked about is instantaneous speed. So this is for, or we can say this is defined at an instant or at a moment of time. So that is equal to, we saw that it is, we can casually define it as delta S by delta T with the condition that delta T should be extremely small. So in terms of measurement, the smaller the value of delta T that our instrument is measuring the distance in, the more accurate our measurement of instantaneous speed is. So if we have a speed gun that is able to measure instantaneous speed by measuring distance by time for a microsecond, it's reasonably accurate. But if something is for a nanosecond, it's more accurate. If something is for a millisecond, it's less accurate in comparison. So then we also understood that in terms of the graphical representation of distance versus time, all this will translate to the language of functions and calculus very soon. But if this is a distance versus time graph, let's say this is distance with respect to time. Now, one is I can calculate this quantity that for some given interval of time, let's say T1 is here on the time axis and T2 is here on the time axis. I want to calculate the average speed. Okay. So average speed from T1 to T2. So that quantity over here, what it becomes, we already know the formula for it. It is S2 minus S1, or the total distance in that time divided by the time interval. But from the graph, let's interpret what we mean by this. So if this is the time T1, then at time T1, I have covered a distance S1 with respect to the starting of my motion. Okay. So obviously, the starting would have been from T equal to 0, S equal to 0. Whereas at some time T2 like this, let's say, I would have covered a total distance from the start of S2. So now in this interval, how much distance I have covered between time T1 and T2, that is this much distance, this S2 minus S1. In this particular interval of time, T2 minus T1. Now the interesting thing is that graphically you can see that if I were to understand that in this particular graph, what is the meaning of this ratio, S2 minus S1 upon T2 minus T1, then you can clearly understand that from the concept of straight line, that if I were to join these 2 points with a straight line, then the slope of that straight line would be nothing but the value of S2 minus S1 upon T2 minus T1. So we saw that such a straight line is called, technically we call it a secant line. There's a secant line which is passing through these two particular points on the graph, which are at t equal to t1 and t equal to t2. So this becomes the slope of the secant line. Further, you can see that if I just extend this over here, you're getting a right angle triangle where this is your S2 minus S1. This is your T2 minus T1. And this angle over here is theta. So it's basically tan theta for that line. Okay, whereas the same thing if we want to interpret instantaneous speed, you don't need to note all this down again because you have seen this in the previous lecture. I'm just doing a quick recap of that concept so that you are able to connect it with differentiation that we'll learn further today. Okay, it's always important to connect the theoretical concepts that we are learning with some practical examples we have discussed earlier. So again, for the same distance versus time graph, let's say, which I had practically recorded for some journey. Now I want to find instantaneous speed. At some time, t equal to t, let's say. So let's say the instant I'm talking about is over here. So at this particular moment of time, I want to find out what the instantaneous speed was. So for that now, what I'll have to do is in our sort of everyday definition of instantaneous speed, not the calculus definition, but the everyday definition, it was delta s by delta t, that is distance upon time, but for a very small interval of time. So this should be extremely small. So as you saw, this extremely small is a relative term. Compared to 1 second, a millisecond is extremely small. But then compared to a microsecond, a millisecond is not small. In fact, it's larger. So the microsecond is the interval which is extremely small compared to millisecond. So it's a relative term. Okay. But okay, loosely speaking, we can say that, okay, if this is our time axis, okay, you can see that compared to the total time of the journey, if I take a reasonably small interval of time, like something like this over here, such that the second point is quite close to the first one. So it is a small interval. Then during that time, the corresponding distance traveled will be also small, but their ratio is what we are more interested in. So their ratio will come out to be the slope of this line joining these two. So this sort of line. Now what happens is as we make delta t smaller and smaller, the second point that I've drawn almost merges with the first point. So if it merges with the first point perfectly, then this is called a tangent line. And we don't have a formula directly for this, so that's where differentiation comes in. But technically this becomes what? It becomes the slope of the tangent. And the smaller the value of delta t that we've taken in the graph, the more accurate our drawing of the tangent is. Okay, so this all of course, you can say sort of abstract, okay, because we are just talking about something which we can imagine that delta t is extremely small. So the 2 points are almost merging. So we are getting a perfect tangent line almost. Okay. But as yet, we don't have any formula or way of calculating this. Whereas for average rate of change, you can see we have a direct formula. We have S2 minus S1 upon T2 minus T1. So that is where the business of differential calculus comes in. A differential calculus gives us an operator or a mathematical operation that will help us calculate, or that will give us a method to directly calculate the instantaneous rate of change. Okay. So that's where differential calculus comes in. So it's a new branch of maths, part of the overall branch called calculus, which is to do with calculation of instantaneous rate of change. So it gives us an operation to calculate the instantaneous rate of change. And now when we're talking about instantaneous rate of change, we will generalize the definition. It need not be only distance with respect to time, which will give us the instantaneous speed, but it can be any quantity with respect to any other quantity. Like we had seen that in physics, there are so many definitions which are based on the concept of rate of change. Now, the net force is equal to rate of change of momentum. The velocity is rate of change of displacement. Speed is rate of change of distance. Acceleration is rate of change of velocity. And so on and so forth. Like, as we go on further, we will learn more quantities like this. Okay. So instantaneous rate of change of any physical quantity with respect to another quantity becomes an extremely important type of definition in physics. So when we talk about differential calculus, the operation, it is an operation to calculate instantaneous rate of change of any quantity with respect to another. Okay. Or you can say any parameter or any variable with respect to another. So in this case, let's say instantaneous rate of change of any dependent variable. So I'll explain this term again, dependent variable. Let's say y with respect to an independent variable. Let's say x. Provided, of course, y is a function of x. That is, there's a relationship between y and x through some kind of mathematical definition, which we call a function. So provided we have two variables, one the independent variable x and the other the dependent variable y, related to each other by some kind of a rule or some kind of a relation, and that type of relation is called a function. So if we have a variable y linked to another variable or dependent on another variable x through a function, then differential calculus gives us an operation that will help us calculate, or that will rather calculate for us, the instantaneous rate of change of y with respect to x. Okay. So we had seen that a function, it is simply speaking a relationship, a maths relation between an independent variable. And typically we take it as x and a dependent variable. So the convention that we use for writing a function in short form, this is the symbolic representation of function. So the convention that we take is whatever variable is on the left hand side, that is the one which is dependent, because its value depends on the value of x. So x here is what we call the independent variable, because x's value is chosen freely without considering anything about y. But once we have selected a particular value of x, the relationship between y and x, which is the function, tells us what the value of y is. Okay. So any sort of mathematical expression or mathematical relationship that relates one variable with another, and therefore the one on the left hand side becomes dependent on the value of the one on the right hand side, which is independent, that is called a function. So we've seen that there are various types of examples of function, like something like this is an example of what we call a quadratic function. This is a different type of function we are seeing today. This is something called a hyperbolic function, or because its graph, when we study later, will be something called a hyperbola. Okay. This is an example of a trigonometric function. This is, for example, again, square root function. Talking about something simpler, this is an example of what we call a linear function. So this graph is going to be a straight line. So there are so many different types of functions. Okay. But in all of them, remember, the convention that we use is whatever variable is on the left hand side is the dependent one, and whatever variables expression is written on the right hand side, that is the independent variable. Okay. So in this you can see that functions of various types, like the ones I've listed, can be expressed by mathematical equations, or in simple terms, relations. Okay. There is a bit more of technicality to this also. We will discuss about that. That technically speaking, certain types of relationships only can be used to describe a function, and certain types of relationships should be excluded from what we can use to define a function. But at this stage, it is enough for us to define a function in this way only, that it relates to variables y and x. Okay, y and x are just the standard names that we use for the variables. Okay, we can always have something like s is equal to, let's say, this. So this is representing now s as a function of time. This is representing this, or t. So this is indicating that t is the independent variable in this case, and s is the dependent variable. But the standard variable names that we use are y and x, like this. Okay. Now, another representation of a function, while functions can also be represented by maths equations, they can also be represented by graphs. Now, when we represent a function by a graph, the only thing we have to be technical about is that the horizontal axis always is the independent variable. We never put the independent variable on the vertical axis. We always put it on the horizontal axis. And why we do that will become clear immediately in some time when we discuss more about rate of change. So the vertical axis always has the dependent variable. Okay. So in another case, for example, suppose I am looking at velocity as a function of time, v is equal to ft, and I'm drawing the graph, then I should not take t on the y-axis. I should take t on the horizontal axis and v on the vertical axis, because this is the independent one and this is the dependent one. So that is, again, you can say a convention or a rule that we always follow for a function. Just like in writing the function, the left hand side has the dependent variable, the right hand side has the independent variable. Like that, in plotting the graph of the function, the vertical axis should always have the dependent variable and the horizontal axis should always have the independent variable. So now, if we plot various points, okay, which satisfy, so suppose we have one particular point x comma y which satisfies this relation, that y is equal to fx. Okay, and then we plot other coordinates of x and calculate the values of y. So we plot all these various different points, okay, and we join them with the smoothest possible curve. So this curve represents the function y equal to fx. Okay, so it is the graph of this function is basically a curve in the xy plane such that all points on it satisfy the relation of the function, satisfy y equal to fx. So simply speaking, that is what we mean by the graph of a function. So we have two ways of representing a function so far. One is through a formula, or what is called the algebraic or maths expression, this one of representing various different functions. And the other way of expressing the function is a more visual kind of representation, and this is called the graphical representation, or simply the graph of a function. All right, so hope it is clear so far. If there are any questions, please let me know. Okay.
Sir,
Yes. Yes, Om.
yes. In an equation where it is y is equal to fx and y is the function of x, it is usually so that x value is given, right?
Hmm.
So what about the equation where the value of y is given? So how exactly will we substitute the value?
You can always do that. That's not a problem. You can back calculate. Now, suppose, for example, I have a function. Suppose I have this function y is equal to, let's say, x square plus 2. Okay. And I give you, if y is equal to, let's say, 1 or y is equal to 3 at some point, okay, then calculate x at the same point. So it's a maths equation. So you can just substitute it and get that. So substitute this over here.
Got it. Yeah.
So 3 is equal to x square plus 2.
Yes,
That will
sir.
be, x square will become 1. So
Yes, sir.
in this case, you will see something interesting, that there are two possible values of x which give you this. Okay. But just because y is given to us and we have to calculate x doesn't mean that now y is becoming independent and x is becoming dependent. Okay. In a general maths expression, it doesn't matter what y and x is. But if we are representing this as a function, okay, so if this is y as a function of x, then still this is the dependent one and this is the independent one. So you can see that there are two values of x, two independent values of x, which are corresponding to the single value of y, which is equal to 3. So
So
that's, yes, beta.
I had it out in instantaneous speed.
Tell me,
If
Sandeep.
we have a graph which is whose line is just slowing down, and if we try to take the instantaneous speed over there, then it would come in negative, right?
Now see, the interesting thing is that, okay, let's understand what you're saying in that sense. Okay. Now think s is distance, okay, not displacement. If s is distance, can we have a situation like this? Yes, definitely we can have a situation like this, okay, because it shows that we are moving in such a way that as time is increasing, our distance from the origin or from our starting point is increasing, right?
Yes, sir.
Okay. Now, if you look at this one, now roughly speaking, if I draw tangent at this point, its slope is something like tan theta for this. If I draw tangent at this point, you can see its slope has decreased. So this is showing something where the instantaneous speed, which is that delta s by delta t, will come back to the calculus definition in a moment. Okay. So in calculus definition, we call it ds by dt, but here we'll just call it delta s by dt, delta t, for delta t being very small. Now that quantity is decreasing as time is increasing. You can see that. Okay. You can also see that the average speed in equal intervals of time is decreasing. But next, if I say the graph is going like this. Now, given that this is a distance versus time graph, do you think this graph makes sense? Distance is basically what? It is the path length, na beta?
Yes, sir.
So can your distance in a forward interval of time, okay, let us say this is, let's say, like 10 seconds and this is 12 seconds, and this distance over here is, let's say, 10 meters, and this distance is equal to 8 meters. Now logically, is this possible that in 2 seconds I'm covering a distance of minus 2 seconds or minus 2 meters? Is this possible?
No, sir.
No, sir.
No. So that means distance versus time cannot have a graph like this. Okay, distance versus time cannot have a graph which has a negative slope. Displacement versus time can have, because displacement has direction. You understanding my point?
Yes, sir. So over there we would get a negative
Yeah,
instantaneous.
there it is possible. Okay, but there the rate of change is what? It is velocity. So as opposed to distance versus time, suppose I plot the graph of the x coordinate of a particle with respect to time. So this is now representing the motion of a particle which is specifically moving along the x-axis only. It's moving along the x-axis. Now it can so happen that the particle started going like this, but after some time turned back and came like this. So here is very much possible that with time, my x coordinate is first increasing, then decreasing, and then coming back to, so now suppose x is back to 0. That means it went to some maximum displacement and then came back to where it started from. So this is possible in this case. Now in this case, what is happening? If we draw the tangent at some point like this, it is having a slope which is negative. So that means v is negative. But in this case, what is v? V is the velocity. So velocity has both magnitude and direction. So the moment the velocity is coming with minus sign, that means the direction of velocity is along the negative x-axis. Whereas somewhere here, the velocity will be a positive quantity. That means the direction of velocity is what? Positive. So here, when we write v as delta x by delta t, remember delta x is, now it is like a displacement along the x-axis. So this is now a vector quantity. So this is now velocity. So that is the difference actually you can see physically between velocity and distance. So velocity time graph, sorry, a displacement time graph can be such that it has a negative slope, but a distance time graph can never, like logically it is not possible that the distance of an object is changing in such a way that it has a negative slope. Hope that answers your question, beta.
Yes, sir.
Oh, very good. Okay, so coming back to functions. Okay, now we come to the all important thing of rate of change of a function.
Sir,
Yes.
sir, we can't have a straight line graph for average speed and instantaneous speed.
Can't have a straight line graph for, you mean the function can't be a straight line?
Yeah.
It can be a straight line. If the function is a linear
In case
function,
of a linear
it will be a straight
equation.
line only. Okay. It will be a straight line. So it all depends. No? For example, if we are plotting distance versus time and the motion is such that there is no acceleration, then obviously distance versus time will be a straight line graph. You're following?
Yes, sir.
Okay, so that all depends on the actual, physical situation we are representing. A graph of a function can even be a horizontal straight line. In fact, we'll discuss about that today. That kind of a function is called a constant function. Okay. All right. So again, talking in terms of rate of change, there are two types of rate of change: average rate of change. So average rate of change is for an interval, but in this case, we will say interval of x. Okay, let's say x equal to x1 to x equal to x2. So this is defined as, now in language of calculus, we will define average rate of change as delta y by delta x. That is the change in y upon change in x, where the change in y is y2 minus y1. The change in x is x2 minus x1. Notice that I'm not putting any condition on delta x, that delta x is very small or anything, because that's not the case. Here I'm talking about delta x being a change from x1 to x2. Okay. So further, formula wise, what this becomes, now what is y2? It is the value of the function at the point x equal to x2. So we can write it as f of x2 minus f of x1 divided by x2 minus x1. So as we saw, this is the simple formula that we have for average rate of change. We don't need anything else. So given any function, so for example, I have the function y is equal to square root of x, and I say calculate the average rate of change from x equal to 1 to x equal to 4, let's say. Okay. So what we'll do here is the function that we'll substitute is square root of x. Okay. The value of x1 that we have is 1. So the value of y1 is f of x1. So that will become, substitute x as 1. So it's square root of 1 or 1. The value of x2 that we have given to us in the question is 4. So y2 is equal to f of x2. So that will become square root of 4, which is 2. Now remember, it's not plus minus 2, it's just 2. So the average rate of change, which will now denote as delta y by delta x by formula, equals to y2 minus y1 upon x2 minus x1. In this case, it's becoming 2 minus 1 divided by 4 minus 1. Okay. So that is 1 by 3, or we can say approximately 0.3. So this is becoming my average rate of change. Okay. So make a quick note of this example and try out another one.
Sir, but why can't we take root 4 as plus minus 2?
Because it is not beta. Okay, that is the mathematical definition. If I write, okay, y is equal to square root of 4, okay, it means that y is a positive number. Okay, y is positive. Okay, the case where it can be plus minus is that different. If I write y square as 4, that's different to this, because the solution of y square equal to 4 is that y square minus 4 is equal to 0. So y minus 2 into y plus 2 is equal to 0. So y can be 2 or y can be minus 2. So mathematically, you should understand that this equation is not equivalent to this equation. They're two different equations. Are you following
Yes,
better? Okay.
Yes.
Okay. So the next example we'll see y is equal to.
Sir, can you wait for a minute?
Yeah, I'm waiting only. I'm giving you time to solve this next example. Okay. So calculate the average rate of change from x equal to. So we'll take two intervals here, 0 to 1, and next interval we'll take is 1 to 2. In fact, just make a small modification here. We'll make the function 2x minus x square. You'll see you'll get an interesting result when we do this. Okay. So just make a note of the first example if you like and work out the second one. Yeah, Piyu, to answer your question, like you can just work out, write down this question, because this is something, this one, and then start working out this one. Okay. I'll be sending you the full, PDF notes also, so
Yes.
you'll refer to that also.
This is a part you are revising average rate of change.
Sorry, beta, can you speak louder? I can't understand what you're saying.
Sir, you are revising this average rate of change because last class we did it.
Yeah, that's what I said. You don't need to note down everything. You just write down this question and work out this next one which I've given you. This second question which I've given. Just work it out and send me the answers on the text message, please.
Yes, sir.
Okay, Harsh, Manas, correct. Sanvi, correct. Ayan, correct. Bhaumik, your first part is correct, but check the answer for the second part. Okay, so let's work out the solution of this. So A part we will take x1 as 0. So y1 becomes f of x1, where the function itself that we are talking about is this, no? 2x minus x square. So it is 2 into 0 minus 0 square, so it's 0. x2 is 1. So y2, which is f of x2, will become 2 into 1 minus 1 square, which is 1. So now my delta y by delta x for this interval will become just substitution and nothing else. Okay. So 1 minus 0 upon 1 minus 0, which is 1. So that is the the average rate of change between 0 and 1 for this given function 2x minus x square. Now we have to just repeat this exercise for the second thing. Okay. But in the second part, we will take x1's value as 1 and x2's value as 2. So correspondingly, y1, which we've already calculated, is 1. Okay, but y2, which is f of x2, now becomes 2 into 2 square minus 2 square.
So 2 into 2 and minus 2
Sorry,
square.
2 into 2 minus.
Then it will go 0.
Yes, so it becomes 0. That's correct. Okay. So this time when we calculate delta y by delta x.
So this is average rate.
Yes, this is average rate of change, right? So this is, we are still in the discussion of average rate of change for a given function for a given interval. So the moment we are talking about an interval x1 to x2, remember we are talking about average rate of change. So now the numerator is 0 minus 1 and the denominator is 1 minus 0. So importantly, it is minus 1. Okay, the algebraic sign is important. So this is having a rate of change in this interval which is negative. This is having a rate of change in this interval which is positive. Okay.
So x2 is 2, right?
Yeah, sorry. So it's 2 minus 1 in the denominator. That's correct. The value will be minus 1 only, the rate of change, but the denominator, when we write it technically, it should be 2 minus 1. Okay, so hope this is clear to all of you.
Yes, sir.
Yes.
Okay. Now let's come to, again, the most important part of our discussion. Yes, any doubt, Beta?
Can you show the answer again?
Yes, yes.
Okay, sir, thank you.
Oh. Okay, now next, let's come to the more important concept of instantaneous rate of change. For a function y is equal to fx. Now we will see a more technical definition than we have seen earlier for instantaneous speed. Okay, we will see a more technical definition. Yes, Piyu, you have a question, Beta?
Sir, y is equals to fx remains the same everywhere, constant.
No, that is just a representation, Beta. That y is a function of x. No? That is just a symbolic
Acha,
representation. But function तो कुछ भी हो सकता है ना, it can be a linear function, it can be quadratic, it can be sine function, right?
Sir. Okay, understood.
So the thing is, now think of instantaneous rate of change as a definition of an operation, but that operation applies to which kind of thing? It applies to functions. Like other operators in maths like addition, subtraction, division, they apply to numbers, or you can say they apply to systems of numbers. Like for example, addition can be applied to both real numbers or integers or natural numbers. But for example, the operation of square root, it cannot be applied to negative numbers. It should be applied to only non-negative real numbers, okay? Or natural numbers or whole numbers. Okay? So there are things like that, but here we are learning a new type of operation, which is called instantaneous rate of change, which just now we are going to also call differentiation. So differentiation operator does not apply to numbers, it applies to functions. Okay, that is the nature of the operation, right? So that's why we are specifying always that we are applying this definition to what kind of quantity. We are applying it to a function. Okay. So instantaneous rate of change is given a new symbolic representation now. And that symbolic representation is dy by dx. So even though we read it as dy by dx like a fraction, but it's not really like that. It is just the symbol for instantaneous rate of change.
Sir,
Yes.
so we did instantaneous rate of change in last lecture, no?
Yes. So as I said that I'm doing a recap of that concept, but we've just seen like the definition last time. Now we'll see how to apply the formula, etc. Right?
Okay, sir.
So what is the definition of instantaneous rate of change? It is delta y by delta x. Okay. But with a special condition, which we call a limit. Okay. So that special condition or limit is written in this way mathematically, that I'll write it in short form now, that limit delta x tends to 0. Okay. So this thing, this is a special condition, or you can say limit. Okay. That delta x should tend to 0. Now this 10 to 0, what it exactly means is again a little bit abstract. Just like when we say something tends to infinity in maths, we mean that it is such a large number that we cannot compare it with any other large number. Okay, it's larger than anything that we can write or anything that we can express. That's a simple way to express infinity. So like that, when we say that something tends to 0, okay, what we mean that it is so small that we cannot compare it with even the smallest number, which is non-zero. So like, let's say I can write a number as small as 10 raised power minus 20 or 10 raised power minus 50, but now my delta x should be even smaller than that because it is incomparable to any other small number. It is so close to 0 that you cannot compare it with even the smallest number that you can imagine. So on the number line, it is like right next to 0. It's not exactly equal to 0, but it's as close as one can imagine with respect to 0. So that is the meaning of the term limit delta x tends to 0. So how do we calculate it? We calculate it by applying this definition that if I change x by delta x, how much is y changing by? Y is changing by the value of the function at x plus delta x, okay, minus the value of the function at x. The whole thing divided by delta x.
Sir, what is this?
Come again, Meta, what is your question?
So I said, what is this? The definition of instantaneous?
Yes, this is the definition of instantaneous rate of change. Okay. So this is the definition of instantaneous rate of change. So this operation only is called differentiation. Okay, so differentiation or differential calculus is an operation to calculate the instantaneous rate of change for a given function. So you can think of it like an operator. So this is the differentiation operator, such that when we input the function y equal to fx, we put this as an input, the output it gives us is the instantaneous rate of change. That is differentiation operator applied to whatever function y is of x. Okay. So this is the output that we get. So input a function and the output that we get is instantaneous rate of change. Of that function.
So dy upon dx is equals to?
Yes, dy by dx is the differentiation operator applied to the function fx. Okay. So this symbol, it's the differentiation operator, d by dx of something. Now what we are applying it to? We are applying it to the function fx. So what that is giving us? It is giving the instantaneous rate of change of y with respect to x. Okay, but understood this?
Yes, sir. Thank you.
Okay. So as we apply this to more and more, actual examples of functions, and as we learn the various formulae and properties of this operator, this will become more and more clear. But in the beginning, it's very important for us to understand what is the meaning of the operation before we come to the formulae and properties of how to apply the operation is one thing, but another thing is what is the operation exactly giving us. So what is exactly giving us is the instantaneous rate of change. So what is the definition of instantaneous rate of change? Now this is the definition of instantaneous rate of change. This one. Okay. So let's look at an example next. Okay.
Sir,
yeah.
Sir, can you please give a short brief of what you said after limit delta x tends to 0, because I lost my network totally.
Okay, just quickly note this part down. Okay. Just remind all of you that the lecture is being recorded, so you will have access to the recording later also. So if at any point of time you lose connectivity, don't worry, you can always revise that part later from the recording.
So can you please just give a brief of what you said?
Yeah, you just write down this part, I told you. We'll apply it to examples, you'll understand it.
So,
yes.
What have you written just after you have written note?
Just after I've written?
Note.
Okay. Limit delta x tends to 0. See, that is the symbol that we are using here. So I've explained the meaning of this symbol. Okay. LIM is the short form for limit. All right. So what is the meaning of this symbol? Limit delta x tends to 0. It is a special condition, or what we call a limit in maths, okay, or calculus. So the special condition, or what we call limit, is that delta x should tend to 0. Now I explain to you in detail what it means that it tends to 0, right? It means that it's so small that it is almost equal to 0.
But it is not equal to 0.
But it is not equal to 0. It should not be equal to 0, but it tends to 0.
Sir, I have one doubt.
Yes.
In average rate of change, you gave the definition and formula. In instantaneous, you gave only definition. So what's the formula?
But for average rate of change, we already have the formula, na beta? It is this y2 minus y1.
And instantaneous rate of change.
Instantaneous rate of change, we don't have a formula yet. We've just got the definition yet. So we are coming to the formula, right?
Sir?
Yes.
Sir, in exams, will we be provided with a function or we have to
Yeah, of
derive
course. The whole idea is that for a given function, you should be able to find the instantaneous rate of change. And for the instantaneous rate of change, what we have to use? We have to use this whole new set of formulae that we are going to learn, which is differentiation.
Okay.
Understood the point?
Yes, sir.
The
Yes,
whole
sir.
idea of differentiation is that if I give you any function, okay, as part of some question or as part of something you're solving, some problem you're solving in physics, then from differentiation, you should be able to calculate the rate of change. Okay. So now let's see how the definition applies to a given function. Okay. So application of the definition of dy by dx for a given function. So for example, let me take the function this time of y is equal to x cube. And let's see what the definition of dy by dx gives me. Okay. So dy by dx was defined as limit delta x tending to 0, f of x plus delta x minus fx divided by delta x. This is how we had defined it. Okay. So in this case, what is the function? The function is x cubed. So when I solve this further, I should replace the numerator with what? I should replace it with x plus delta x's function is x plus delta x whole cube. And the function's value at x is nothing but x cube divided by delta x. Okay. Now if you see, if I make delta x equal to 0, then this operation doesn't make any sense at all. Because the numerator will also become 0, the denominator also becomes 0, and 0 by 0 is not defined in maths. But luckily for me, I'm not defining delta x equal to 0. I'm saying it's tending to 0. So it might be very, very small. It might be so small that we can't imagine it, but at the same time, it's not equal to 0. So this is still a legitimate operation. It's not an illegal operation because delta x is not 0. If delta x had been 0, then this would have been an illegal operation because we would have got 0 by 0, which is undefined in maths. So that is where the concept of limit delta x tending to 0 becomes very important. Okay. So next step, what we can do is we can expand the numerator. Now we all know the formula a plus b whole cube, right? This is a formula that we are familiar with, right? So we can use this one to expand this term.
Yes, sir.
So this will become limit delta x tending to 0. So when the moment we expand this, you see the numerator will become a little bit more simplified because x cube term will cancel out. Okay. So next step, we can cancel these two. So this and this gets cancelled out. And after cancelling these two, you can see we can also take delta x common in the numerator. So let's do that also. So let's take delta x common in the numerator. So we'll be left with 3x square plus 3x delta x. Right? Plus delta x square divided by delta x. Now next we come to the most important step of this operation. I can divide these two. I mean, I can cancel these two. Why I can do that is because delta x is not equal to 0. It is not equal to 0. It is only tending to 0. Okay. So understand that a by a can be written as 1 for all values of A other than A equal to 0. If A is equal to 0, then A by A is undefined. Okay. So that's why I said that it's important to understand here that delta x tends to 0 means that it's not equal to 0. It's almost equal to 0, but it's not exactly equal to 0. So once I do that, I'm now left with just this, that limit delta x tends to 0, 3x square plus 3x delta x plus delta x square. Now I can see that if delta x tends to 0, this term, this also tends to 0. This term, it also tends to 0. Okay, so I can neglect these two terms and I can say that, okay, practically speaking, this is going to be equal to how much? Is going to be equal to 3x square. So I get the formula that for the function y is equal to x cube, the differentiation operation. So this whole operation that we have done from the beginning to the end, by applying the definition of instantaneous rate of change, this whole operation is called the operation of differentiation. Okay, this is this operation. So this is telling us that the differentiation of the function x cube gives us what? It gives us 3x square. But how we get from differentiation of x cube to the formula 3x square is by applying the definition and applying all these steps. Is this clear now?
Yes, sir.
Yes, sir.
Now the thing is, you might ask that how I'm making these terms 0. So I'll just say, take an example. Okay, suppose if I take the value of x as, let's say, 1, but for argument I take delta x as 0.001. So then see what will happen over here. That term 3x square plus 3x delta x plus delta x square will become 3 plus 0.003 plus 0.000001. Okay, so it will become 3.00301. Okay, this term will become this much. Okay, but now imagine if I take delta x as 0.000001, then when you calculate this thing, you will see you will get it as 3. Sorry, this term will be 3. Okay, so like that, now if I take delta x as, for example, 10 raised power minus 20, so you'll see that you'll get this term as 3 plus 3 into 10 raised power minus 20, okay, plus 10 raised power minus 40. Now for all practical purposes, this is equal to 3 only. And this is still a finite value of delta x, this is still not delta x tending to 0. Delta x tending to 0 is much smaller than that. So for delta x tending to 0, it will become exactly equal to 3 when we take x as 1. Or when we take the x as any general value x, it will become exactly equal to 3x square. So that is the difference between saying merely that delta x is very small versus saying that delta x tends to 0. Delta x tends to 0 is a much more, you can say, it's a much more critical kind of condition compared to just saying that delta x is extremely small.
Can we note down, please?
Yeah, I'll take you back to that. Okay, first note down the steps of this operation fully properly. This part that we've done from here to here, okay, how we applied the differentiation operation by applying the definition of instantaneous rate of change. Just a moment, take you back to that. So first make sure you're clear about these steps here, these ones from here to here. please go through the steps that I've applied over there for differentiation of x cube, how it finally comes out to be 3x square very carefully. And let me know if there is any doubt whatsoever in any of the steps. Okay.
Sir,
Yes.
I have a doubt in the second step.
Yeah, beta.
Sir, how did you get x plus delta x the whole cube?
So see, what is my function? Okay, my function is x cube. So for example,
Yes.
what will be the value of the function at x equal to 2? It will be 2 cube. Okay, what will be the value of the function at 2 plus 0.01 cube? Sorry, at 2 plus 0.01. It will be 2 plus 0.01 cube only, no beta? Understood, no?
So sir, it can't be like x cube plus delta x cube.
No, because what we are substituting x as, we are now substituting x as x plus delta x. So f of x is defined as what? X cube. So f of x plus delta x has to be defined as what? X plus delta x cube. Understood the point, no?
Yeah, so if x plus delta x will become like the value x2, and so the
Yes.
x2 cube.
Exactly. No? So it's like we are doing here, it's like we are calculating f of x2 minus f of x1. Okay, divided by x2 minus x1 only. But here we are taking x1 as x, any general value, and x2 as x plus delta x, and add to that we are applying the condition that limit delta x tends to 0. That this is very small.
Yes. Understood. Thank you.
So
Yes, beta.
I had a doubt in the last step, second last step.
This step where the delta x has been cancelled.
Yeah, so where you have written like it's tending to 0. So over there, that delta x is multiplied with 3x. So that we can't take it as 0, right?
Why? Because so that's what I'm saying, no? That compared to 3x square, 3x delta x will be extremely small.
But sir, it will be something 3 multiplied with something, right? If delta x is 0.0001, it would be something multiplied with 3.
Yeah, but see, that's the point that we are making, na? Like you're imagining 0.001 as a small number, but that is not tending to 0. Like what is the smallest number you can imagine? You can imagine a number smaller than 0.001. Like you can imagine a number like 10 raised power minus 6. Okay, but even 10 raised power minus 6 is not tending to 0, because I can imagine a number even smaller than that, and that is 10 raised power minus 10 or 10 raised power minus 50. So like that you can go on and on. But at some stage you will reach so close to 0 that you're literally on the number line, you're at the next point after 0. You understanding the point?
Yes, sir.
So when you reach that stage, this term will be negligible compared to 3x square.
Yes, sir.
Okay, so that is the meaning of the limit term. You understanding better?
Yes, sir.
Okay.
Thank
So
you,
that's
sir.
why when we apply the limit that delta x tends to 0, then we can apply the condition here that this term 3x delta x, this whole term actually tends to 0.
Sir, so when we use the function of dy upon dx is equal to nx raised to n minus 1.
We are coming to that beta.
Okay.
That is this kind of operation only, but it is applied to the general function x to the power n instead of the specific one, which is x cube. Understood now?
Yes, sir.
Okay. Okay, so now let's look at this point over here on the side which I've written, which is one way of explaining how we are making this term 3x delta x and this term delta x square, both of them tend to 0. Now, if I take a reasonably small value of delta x, okay, I'm not saying it's tending to 0 yet, but I'm taking a reasonably small value of delta x, which is 0.001. And just for example, I'm taking the point x as equal to 1. So then what is the value of this whole thing? 3x square plus 3x delta x plus x delta x square, it becomes this. Now we can see that this is almost equal to 3. But it's still not equal to 3. It's almost equal to 3 because I've neglected the third place of decimal. Okay, I have approximated up to second place of decimal. Now instead of taking it as 0.001, which is basically 10 raised by minus 3, I'm taking delta x even smaller next. Okay. Now next I'm taking delta x as 10 raised by minus 6, as you can see. So you can see that the value of dy by dx, or this whole term, it comes even closer to 3. Because now if I approximate up to fifth place of decimal also, I'll get it as 3 exactly. Okay, now imagine what if I had taken delta x as 10 raised by minus 20. Then you can imagine how much closer this whole term is coming to 3. Okay, and like that, if I now take delta x tending to 0, you can see that this term has actually become exactly equal to 3. We are not approximating it as 3, but it's exactly become equal to 3. So you can see that the smaller the value of delta x that I take, the closer I'm coming to this term becoming equal to 3x squared. So if I take it tending to 0, it means it becomes exactly equal to 3x squared. Okay, is this clear, people?
Yes, sir.
Okay. Now before we come to the formula of differentiation, okay, let's again understand what we mean by. So in this example, we saw that if y is equal to x cube, okay, then by applying all that process of differentiation, we saw that we get this as, by applying the definition, we get this as 3x squared. Now, what is the meaning of this thing that dy by dx is equal to 3x squared? It means that the instantaneous rate of change of y with respect to x for the function y is equal to x cube. So this thing equals to 3x squared. So that means that at any point, let's say x equal to a, where a is some specific value, okay, the slope of the tangent, okay, is equal to 3a square. So let's understand that with an example. So if you think of the graph of y is equal to x cube, you can understand it's a curving graph because y increases very rapidly with x. Okay. So I'll come back and you can note this point, but let's just visualize this on the graph first. Okay. So if I'm plotting the graph of y is equal to x cube, you will realize that it's graph that tends to increase rather rapidly like this. Okay. Because if you see at x equal to 1, the value of y is 1. But for example, by the time we reach x equal to 2, it's rapidly increased to 8. By the time we reached x equal to 3, it's more rapidly increased to 27, and so on and so forth. So now the meaning of this term that dy by dx is 3x squared. So for example, if we take at x equal to 1, the value of dy by dx is equal to how much? It is 3 into 1 square. So it is equal to 3. So what this means is that at x equal to 1, the slope of a tangent is equal to 3. So that means at this point, if I draw this tangent line, okay, so this tangent will have a slope equal to 3. Okay. Now if I compare this to another point, like let's say I arbitrarily take some point like 5. So for example, at x equal to 5, dy by dx's value will become 3 into 5 square. So that's 25 into 3, so that's 75. So that means that at x equal to 5, the slope of tangent is equal to 75. Okay. That means at this point here, if I draw a tangent line now, this tangent will have a slope of 75. That is so much more than this. Okay. So you can see the nature of the graph, how it's correlating with the slope of the tangent at given different points. Okay, because the graph is curving very rapidly like this. That is why if I draw a tangent at one point like this and compare it with a tangent at a point slightly later, you can see the slope of the tangent is increasing very rapidly according to this formula 3x square. Okay. So
Sir,
this is, yes.
sir, so dy by dx is constant to 3x square.
कैसे constant हुआ बेटा? 3x square कैसा quantity? Is it constant or is it variable?
Sir,
It depends on the value of x, ना? But if I
हर बार dy by dx हम 3x square ही लेंगे मतलब ऐसे.
नहीं, वो कहाँ बोला मैंने बेटा? ये तो इंस्टेंटेनियस रेट ऑफ चेंज है फॉर द पर्टिकुलर फंक्शन y इक्वल टू एक्स क्यूब ना. अगर मैंने फंक्शन कुछ और लिया तो द वैल्यू विल नॉट बी 3x स्क्वायर ना.
सर फंक्शन y 3x. ठीक है सर.
अंडरस्टूड ना? Like last time we had
Yes,
taken
yes.
example of the function y is equal to x square, right? And dy by dx had come out to be how much? It had come out to be 2x, remember?
Yes sir, yes sir.
So now we'll see that there's a pattern, there's a formula for this. We'll come to that also. But so far what we've discussed in the above example, that for the function x cube, when we apply the differentiation operator, we get the formula 3x square. Now what is the meaning of this formula 3x square? The meaning of this is that if I want to calculate the slope of tangent at any point, like 1, 2, 3, 4, 5, or any other point, even a fractional point like 0.5, I have to substitute the value of x as that value in this. And then what the value that I will get by substituting x as e or whichever specific point like 1 or 5 or whatever, that value will be nothing but the slope of the tangent at that point. Is it
So
clear now? Yes.
what is slope of the tangent? Like you say over here slope is equals to 3. So what does that actually mean?
So see, the tangent is a line, no?
Yes, sir.
So whatever the curve is, the tangent is a line like this. Now for a given line, what is the slope? It is tan theta.
Yes, sir.
Okay, so that is the meaning of this. So if you compare this red colored tangent that I've drawn at the point x equal to 1 with respect to the second tangent that I've drawn at x equal to 75, you can see they are having different slopes, no?
Yes, sir.
So here, the way I've drawn these two, you can see theta prime is greater than theta. So that means the slope of the second line is greater than the slope of the first line.
Okay,
if
sir.
this is line number 1 and this is line number 2. So the comparison of the two is telling you that this one has a steeper slope. That means it makes a larger angle with the x-axis. Okay, beta, you're following this now?
Yes, sir.
Okay.
Sir,
Yes.
this means that dy by dx is equals to 3x square is only applicable when y is equals to x cube.
When y is equal to x cube, correct, of course.
Okay, sir.
So because differentiation process has shown us ना कि y जब x cube होता है तो उसका instantaneous rate of change कितना हो जाता है 3x square होता है. How we came to know that? By applying that definition, right?
Yes, sir.
Okay. Any other question about this? This is clear?
Can we note down?
Yeah, you can write this down. So you can write down this general concept first. Okay. Sorry, this part.
Sir,
Yes.
sir, can you please just re-explain the statement for differential calculus?
Sorry, come again, Vita. Could I?
Can you please just re-explain in brief the meaning of differential calculus? What
Yes.
operation exactly?
We'll do that. We'll do that. Okay. Manas, to explain specifically, we don't calculate dy from the slope beta. Okay, dy by dx is not actually a fraction, so it's not like it is something divided by something. Dy by dx is an operation which gives us the slope of the tangent. You understanding?
Sir, because we are not taking sir y value in consideration, we are mostly taking x. That's why, sir, I was asking.
So we are taking y in consideration, no, beta, because y is a function of x. So the relationship between y and x only is helping us calculate that what is the rate of change. Because y is equal to x cube in this case, that is why the rate of change is equal to 3x square. If y had been some other type of function of x, then we would have got a different relation, no, for dy by dx. You're following?
Yes, sir.
Okay. Okay, so now what we'll see is that
Sir, can you scroll up for just a second?
yeah.
Sir,
Yes.
the example green one you wrote below,
Yeah.
why you apply the condition 3x square? It is not given no y is equals to x cube, then why you applied?
No, it's the dy by dx beta. It's not y.
Okay, sir.
You understand? The y's value is your correct. It is 125. The y coordinate at this point will be 125.
Okay, sir.
At x equal to 5, this coordinate is 125. But what about the slope of the tangent? The slope of the tangent is 3x square, no? So it will be 75. You understood the difference between the two?
Yes, sir.
Okay. Now next we'll see that there is a general formula for differentiation, so that every time we don't have to. Okay, just a minute, guys. I'll just join you. Just give me a minute. Okay, so now having seen these couple of examples, okay, of application of this definition of instantaneous rate of change. Okay. Now let's come to the general formula for differentiation of x to the power n, where n is any real number. So that is given by this simple relation, n into x to the power n minus 1. Now, where this formula has come, it has come from the same type of derivation that we did for specifically for y is equal to x cube just now. Okay. So if we do that same type of derivation, but using the power of x as n instead of 3, we'll get this general formula that it is nx to the power n minus 1. But now the derivation of the formula is not important for us immediately. Okay. We will look at the derivation at a later stage. Okay. Those of you who are PCM students or PCBM students, you will also look at the derivation of this formula in your advanced calculus course in maths. Okay. Whereas for PCB students, I will give you the justification of this towards the end of the course of differentiation that we are doing right now. But for us right now, what is important is not the derivation. It is important how to apply this function. So for example, for n equal to 2, we have the function y is equal to x square. So differentiation of this function from this formula comes out to be 2 into x to the power 2 minus 1 or 2x. So this tells us that differentiation of x square is equal to 2x. Okay. For n equal to 3, if we apply this, we just saw that differentiation of x cube, by that lengthy derivation we saw by applying the limit condition, after many steps it was coming as 3x square. Okay. Here we can see that by applying the formula directly, it is justified to be 3x square. So just make a note of the formula in these two examples first. Okay. Then we will see more interesting values of n, like fractional values or negative values.
Sir,
Yes.
sir, this y is equals to x2, where you have applied this, substituted this value.
Sorry, come again. This y is equal to
x2, this is there now. You have written in first example, y is equals to x2.
X square, yes.
X square, sorry. So, sir, where you have substituted this value?
I have substituted here, no? From y equal to x square, dy by dx is equal to what? It is the differentiation of the function x square. Okay. Now x square, if you compare it with the general formula, it is x to the power 2. No? So in the general formula, what is the power of n? Of x, it is n.
Yes, sir.
No? So you understood now. So this term is x to the power n, where n is equal to 2. So that's what's happening over here. See this right hand side of the formula? It is n into x to the power n minus 1. So understood now how we have applied the formula?
हाँ सर वो पता चला, मैं पूछ रही हूँ y is equals to x square आपने कहाँ लिखा है? See, because the formula is d upon dx in the bracket x raised to the power n, so that you have written full.
So what
Y
is,
equals to x
see, what do we
square.
differentiate? We differentiate the function, na? Y is equal to x to the power n. You understand? So this is dy by dx only, no, beta?
हाँ sir.
Understood, no?
हाँ sir, okay.
So this formula that we have written here, na, it is specifically for which type of function? When y is some kind of power of n, some kind of power of x, that power being n. So whenever y or the function is of this type, it's a single power of x, where that power could be any real number, then the differentiation operator's formula is that it is n into x to the power n minus 1. So for example, if I take n equal to 2, the function that I'm getting is y is equal to x square.
Sir?
So according to this formula, the differentiation of that function or dy by dx should be how much? It should be 2x.
Sir?
Similarly, if I take n equal to 3, just a moment, the function is y is equal to x cube, then dy by dx according to the formula should be how much? It should be 3x square. Okay, is this point clear, beta?
Yes, okay, thank you.
Yeah.
Sir,
Yeah.
what is this 3x square? It is a function.
Yeah, but it is a function which is giving us the rate of change of the first function. You understanding?
Yes, sir.
So for example, if I like I saw over there, that if I draw the graph of y is equal to x cube, now at a point x equal to 5, what is the slope of the tangent? It is 3x square's value at x equal to 5. So it's 75. What is the slope of the tangent at x equal to 2? It is 3 into 2 square. So it is 12. Okay, so let's do some more examples. So if we have y is equal to square root of x, now I want to find dy by dx. Okay. So this is another example that I will solve for you, and then I'll give you an exercise to try some of your own. Okay. So y is equal to square root of x.
Sir?
Yes. Tell me.
Sir, in the previous example where n
Yes.
is equal to 3, at
Yes.
there at the end 3x square is a result of 3x raised to 3 minus 1, right?
Yes, exactly. This operation has been applied.
Yeah, so that was figured out.
So now in this case, square root of x means I can also write it as x to the power half. So it basically means y is equal to x to the power n, with n's value specifically becoming half. So differentiation of y with respect to x, I will now express as differentiation of x to the power half. So that will be n into x to the power n minus 1. So that will become 1 by 2 x to the power minus half, which I can also simplify and write as this, or I can write it as this. Okay. So dy by dx here, which is differentiation of x to the power half, by application of this formula finally comes out to be this. So this becomes our final answer for this question. That what is differentiation of the function root x? It is 1 by 2 root x. So note down this example and try out these following questions next.
Sir, how you got 1 upon 2x to the power half?
Okay. So here we are going to use some simple principles of indices. Okay. That is 1 upon x to the power a can be written as x to the power minus a. Okay. For example, x to the power minus 2 is 1 by x square. Okay. X to the power minus half is 1 by x to the power half. Okay. So these are the simple rules of indices in algebra, right? Is it clear, beta?
Yes, sir. Yes, sir.
Okay, just find out dy by dx for these following.
I have a doubt.
Yeah, beta, tell me.
Sir, in your example third, at the last part, you written 1 upon 2 x raised to the half.
Yes.
So in next step, how come it becomes 1 upon 2 root x?
बेटा ये तो डिफरेंशिएशन है ना, ये जो स्टेप है ये डिफरेंशिएशन ऑफ x टू द पावर हाफ है ना, तो वही तो हमने ऊपर वाले स्टेप में दिखाया है, वो कितना बन रहा है 1/2 रूट x. दिस होल सिंप्लीफिकेशन इज दिस ओनली ना. Okay, so please send me the answers on the text message for each of these parts. Anybody got the answer for each
Sir,
part?
can you once shift your
Yes,
screen
sir.
towards
Yes, sir.
upwards?
You want to see the previous part, the formula?
हाँ sir, 1 minute.
Okay.
Yes sir.
This formula, na? Okay.
Just a minute.
So differentiation of x to the power n is n into x to the power n minus 1. So that is the formula to use.
Sir, the answer can be negative.
Yeah, it can be negative. No? Like we saw, slope of the tangent in general can be negative. No?
Yes sir, you can move towards the question.
Oh. So the first step in each of these is now you will have to express them as a single power of x. So for example, 1 by x, you will have to express it as x to the power minus 1, correct? Then apply the formula. Then
Sir, why like this?
sorry,
So why x raised to -1?
because we just saw na that 1 upon x to the power e is the same thing as x to the power minus a, rule of indices. Okay, so 1 by x is the same thing as x to the power minus 1.
Oh, okay, so yes, sir.
Got it, no? So because we are using this formula, na, the differentiation of x to the power n is n into x to the power n minus 1. So ये formula को apply करने के लिए I have to reduce the function to this type now, where it is some power of x. So right now it is 1 upon some power of x, that is it is 1 upon x to the power 1. So how I'll reduce it to x to the power something? By bringing this to the numerator. So when I bring this to the numerator, the power will become minus 1.
Yes.
Like that. Okay, now like that, some more rules of indices we will use is that x to the power a into x to the power b can be reduced to what? X to the power
A
e plus b. So that is the second rule of indices that we use. Okay, and similar to this is the third one, x to the power e divided by x to the power b. None of the functions have this one here, but in general it is e minus b. So these are some of the common rules of indices that we'll be using in these type of differentiation problems. Right? So at the moment, what will happen is that differentiation and calculus in general will look like more like mathematics to you than physics. So many of you might be wondering why we are studying this in physics. But the idea is, see, physics always speaks in the language of mathematics. Okay, till date, the physics that you've done, the mathematics that you've used is simple arithmetic like addition, subtraction, calculation of area, volume, things like this. Okay, but in 11th, 12th, the physics becomes a little bit more technical. So the language of maths that physics deals with will also include two other important aspects of maths, and one of them is calculus and the other is vectors. So that is why the beginning of our physics course is with vectors and calculus. However, we will teach it in such a way that always, once we learn a bit of the maths, we will see how its application happens in physics. Okay. So right now, differentiation will, for 1 or 2 lectures more, it will seem like pure maths. But the moment we've learned some of the basics, we will again see how differentiation is applied in actual physics problems. So just have to be a little bit patient at this stage.
Sir,
So very good. I'm getting correct answers. Sanya, your answer is correct. Sanvi, your answers are correct. Okay. Siddharth, correct.
So can
Ayan, check your. Yeah. What beta you want me to?
solve the first one.
First one. Okay. So I'll. Okay. So let's see each of these questions now. So these are the questions, and in general, we'll be using this formula that differentiation of x to the power n is given by nx to the power n minus 1. Okay. So for example, the first one here, we will first of all express it as x to the power minus 1. So differentiation of y with respect to x is the differentiation operation applied to the function x to the power minus 1. So if you compare with this formula here, you can see the value of n is minus 1. So it should become n, that is minus 1, into x to the power n minus 1, that is minus 1 minus 1. So that is minus of x to the power minus 2, or that can be written as minus 1 by x square. Okay. So we can see that this is the value of dy by dx for this particular function. Okay. Likewise, for the second one,
sir, -1 upon x square, how it is?
okay, so again, see, we are getting minus 1 into x to the power minus 2. Okay.
Yes, sir. Yes, sir.
So we again using that rule of indices.
So we will bring back that. Okay. And
Okay, this is the rule of index now, that x to the power minus
so
a.
we have to
is,
convert it into the same. We can't keep it like this, like minus.
you can
x
keep it like
raised to
this
the
also,
power.
beta, but remember, see, you are going to get MCQ questions na, in your exam. So you have to match it to the option. Na? So the option might be given in this form also, the option might be given in this form also. So you have to know how to interconvert. You understanding my point, na, beta?
Yes, sir. Okay, I got it.
I might have solved it correctly as minus x to the power minus 2, but out of the 4 options given in the exam A, B, C, D, none of them are matching because the option is given as minus 1 by x square. So I should not get confused then. I should know how to convert this. Okay, so this is very important.
Yeah. Thank you, sir.
Okay.
So, sir, how exactly will we convert x root x?
Yeah, so I'm coming to that. So x root x को मैं कैसे लिख सकता हूँ? X into x to the power half.
X upon 2. X raised to x upon 2.
नहीं, क्यों x raised? See what I'm doing है ना? Root x क्या होता है? X to the power half होता है?
Yes.
है ना? So x into root x is the same thing as x into x to the power half. Now x itself is like x to the power 1, right? So this will become what? X to the power 1 plus half. Okay, is this second step clear now?
Yes, sir.
Okay, so this is basically what? X to the power 3 by 2. So y is equal to x root x implies that y is equal to x to the power 3 by 2. So differentiation of y now is differentiation of x to the power 3 by 2. So now we'll apply the formula again. So it is n, that is 3 by 2 into x to the power n minus 1. So that is 3 by 2 x to the power half. Okay. Now this answer is also correct, but we can simplify it a little more and we can write, or rather than simplify, I can say we can express it such that x to the power half is written as root x. Okay. So both these answers are correct. The first one is also okay, but we should know that this is equivalent to this one.
So this value is constant of root x, which is half.
Sorry, come again. This value is?
How we change that root x is half, x raised to half.
You're asking how we know that?
No, sir, it is constant or
no, it depends on the value of x, na beta. So again, graph में अगर मुझे tangent draw करना है at the point x equal to 1, so the slope of the tangent will be how much? 3 by 2 into square root of 1. If I want to draw the tangent at the point x equal to 100, no, it will be 3 by 2 into square root of 100. Understood?
Yes.
Okay. So in general, for the function y is equal to x root x, the instantaneous rate of change at any point x is how much? 3 by 2 root x. So if that point x I'm taking is 1, then dy by dx's value is 3 by 2. If that point I'm taking is 4, then dy by dx's value will become 3. Got it, no?
Yes, sir.
So this gives us a formula. The differentiation gives us the formula for the instantaneous rate of change at any instantaneous point, that is any particular point x equal to x. Okay, so most of you who have sent the answers for the C and D part have got it correct. Okay, but anyhow, I'm just working out the steps for your benefit. Okay, so C part we have taken y as how much we have taken 1 by root x. Okay, so first step is the simplification. So this means we can write y as 1 by x to the power half, or
X raised to minus 1.
Yes, very good. So now when we are differentiating, we have to apply the differentiation operation to the function 1 by root x, but that function is the same thing as x to the power minus half. So now we can apply the x to the power n formula directly. So that will become n into x to the power n minus 1. So that is minus half into x to the power minus 3/2. So this is also correct, but we can also write this as x to the power 3/2
Sir, minus 3/2 will not come.
minus था बेटा, इसीलिए I took it to the denominator ना.
Yes, yes.
Okay, so hope the first three parts are clear to all of you, A, B, and C. Now let's come to the D part. So D part is basically which function? It is the cube root function. Y is equal to cube root of x. So by definition, that means y is equal to x to the power 1/3. This is called cube root of A. So for example, cube root of 8 is 8 to the power 1/3, which is 2. Cube root of 1000 is 10. So like that. So anyway, so once we have reduced it to a single power like this, now we can apply the differentiation operator on it. So 1/3 x to the power 1/3 minus 1. So this we can further simplify as this. Okay. So this becomes our answer. Or if we want, we can simplify this further and we can write this as cube root of x square.
Sir, this last line I not understood.
Okay, power minus 2/3 is clear, beta. कैसा है? 1/3 minus 1 is minus 2/3.
Yes, sir.
So that we are bringing to the denominator now. Okay.
Okay, sir.
So this term here only is minus 2/3. Okay, so hope these 4 examples are clear to all of you. We've almost come
Sir,
to
how did you get the final answer?
that one. No? Okay, I'll explain. So see, we had this thing. No? We had x to the power 2 by 3 in the denominator, right? So this can be written as x square to the power 1 by 3.
Yes.
Right. So that can be written as cubic root of x square. Okay. So that's how I got that 1 upon 2x to the power 2 by 3 can also be expressed in another way as 1 upon 2 into cubic root of x square. Sorry, 1 by 3 into, because so this is just another way of expressing it. It's not necessarily, it's not like we are simplifying this. It's just another way of, because they are equally simple. Whether we write it as x to the power 2 by 3 or cube root of x square, it's equally simple. But it's another way of expressing the same thing. Okay. So this is something that you will, become confident with practice. Don't worry. Okay. These rules of indices and all, I'll make you practice enough that you will get comfortable with them. The more important thing is the differentiation step. How we apply x to the power n's differentiation as nx to the power n minus 1. Yes, PU.
So you have given till now 3 indices, no?
Sorry, I have?
You have given till now 3 indices, no?
Yeah, this is all part of the principle of free indices. Okay, now before we conclude, we will see one more property of differentiation. Okay. This was the formula. Now we'll see another thing, which is the properties of differentiation. Now there are quite a few properties, okay, but we'll start with basic property today. Okay. And the first of the basic properties of differentiation is differentiation of a constant is equal to 0. And this is just logical, because if y is equal to a constant, okay, that means, actually, technically speaking, you can say y is not a function of x anymore, because its value does not depend on x. But still, if you want to see the relationship between y and x in a graph, that same thing will be represented by a horizontal straight line, because no matter what the value of x is, the value of y is remaining the same. It's remaining whatever that constant is. Okay. So for example, if I have got this function that y is equal to constant, and that constant's value is, let's say, 5. Okay. So there's an example of this, y is equal to 5. Okay. So basically y is a constant where that constant is equal to 5. So now I can see that if I draw the tangent line at any point, or if I calculate the rate of change between any 2 points, whether I'm taking x1 and x2, or I'm taking 2 points which are very close to each other, such that this is delta x tending to 0. Whichever of the two I'm doing, I can see the rate of change will be 0. Okay. It's.
So what is this y is equals to 5?
This is an example of the constant function. Y is equal to 5 is a constant. Okay.
Okay, sir.
So if I take the value of c as 5, the graph will look something like this, where this point on the y-axis it cuts is 0, 5, but any other point on it is any x coordinate, but the y coordinate is 5. So the rate of change of this function will always be 0. No? This is limit delta x tending to 0, f of x plus delta x minus fx divided by delta x. But this is just going to be, now whatever the value of x, the y coordinate is 5 only. No? That's 0. Okay. Or the slope of the tangent you can see is 0. So that's the first property, that differentiation of a constant is 0. If instead of x to the power n I have a constant, then obviously the rate of change is equal to 0. So the logic of that you can understand either from the graph. The graph of a constant function y is equal to constant is a horizontal straight line, so its slope is obviously equal to 0. Okay. Or you can understand logically like this, that dy by dx is change in y upon change in x for delta x tending to 0. But if y is a constant, then the numerator is 0 because its value just doesn't change. Right? Is this clear to all of you?
Sir, if a constant is given, we no need to calculate, right?
Yeah,
we can
no
write
need
it.
to directly its differentiation is 0. You don't need to do all this. You can directly use this formula or this property that differentiation of a constant is 0. Okay, is this clear?
Yes, sir.
Yes, sir.
Sir, that graph, can you explain me once more?
So if I have the function y is equal to 5, okay, so how will the graph of it look? All the points on the graph should have the y coordinate equal to 5, no?
Yes.
So it should be a horizontal straight line.
Okay.
So,
yes.
What have you written on the inside the bracket near if y is equals to c?
Where c is equal to 5. Okay. C is a constant. This one here, constant.
Yes, sir.
Constant. C is a constant.
Sir,
yes.
So if the rate of change is like the speed, so then if it is a constant, then the acceleration will be 0, right?
Correct. If your y is speed, okay, if you're plotting speed versus time and the graph is a straight line, so what this is showing you, that speed is constant. So what that is showing you, that rate of change of speed, later in kinematics we'll see that rate of change of speed is acceleration, so that is 0. Right?
Yes.
Okay. Now the second property quickly we'll understand. Okay, differentiation of a constant multiplied by a function is given by, you can take the constant outside and directly differentiate the function. So let me explain this with an example. Suppose y is equal to 3x square. Then how to find dy by dx? So here dy by dx will become differentiation of 3x square. Now when I look at the quantity 3x square, 3 is a constant and then I multiplied it with the power of x. Now I know the formula that differentiation of x to the power n is equal to nx to the power n minus 1. So from this I know that differentiation of x square is equal to 2x. Okay. But there's also 3 multiplied. So what do? I use this property. So I use this property over here. 3 is a constant. So I bring 3 outside the operation. So it becomes 3 multiplied with differentiation of x square. Then I use this formula and that becomes 3 into 2x. So it becomes 6x. So in this case, the differentiation of y with respect to x will become 6x because y is equal to 3x square. Okay. So like this, any constant multiplied by a function, if I'm differentiating it, the constant comes outside. Is the example clear, people?
No, sir, not in this.
Okay, so just follow the steps that I've applied over here. What is y related to x as? It is 3 into x square. Now what is 3? It's a constant, right? It does not depend on x. Is it clear?
Yes, sir.
Okay. And what is x square? It is a function of the type x to the power n.
Yes, sir.
So when differentiating 3x square, what is the first step we'll do? We'll take the constant outside the differentiation operator. So 3 is the constant. I've taken it outside.
Yeah.
Now it's clear?
Yes, sir. Now.
Sir,
Yes.
sir, will you post the solutions for the last assignment you
Yes,
gave?
yes. I will be sending the hints and answers for that. And I will also be discussing those questions in the next lecture that we'll do. Some of the questions particularly I want to discuss in class. Okay.
Sir, in the second example, we are basically removing the constant and solving as we do. Then in the end, we multiply the constant with the answer, right?
Exactly. We are just applying this property of differentiation. That differentiation
Sir,
of any constant term multiplied by a function is the constant multiplied by differentiation of the function. So differentiation of 3 multiplied by x square is nothing but 3 multiplied by differentiation of x square. So that's 3 multiplied by 2x. So that becomes 6x. Clear?
Yes, sir.
Okay.
Sir,
So very good.
f of x here it is 2x.
No, beta, f of x here is x square na, in the example. See? What quantity we are differentiating? We are differentiating 3x square, na, beta?
Yes, sir. Sir, you can explain me that red box which you made at last with the tick, that one.
This one?
Down one. Yes, sir. This one.
ये तो डायरेक्ट है ना बेटा. डिफरेंशिएशन ऑफ x स्क्वायर मैंने यहाँ पे दिखाया कैसे होता है. You done that 2 times earlier also today. Differentiation of x square is 2x. You understood how this comes?
That with the formula I understood.
Okay. So that's how this term becomes 3 into 2x now, because this term, this is replaced with 2x. So it is 3 into 2x. Got it now?
Okay.
So, sir,
Yeah.
it would be 4 instead of 3. We would write 3 into 2x, which is 8x, right?
Sorry? Come again if?
Sir, if there would be 4 instead of 3. So we would write
Whatever that constant. Yeah, correct. So suppose,
8x.
okay, so let's take another example to clarify this. Now let's change both the things. Now let's say that this is 4 instead of 3, and this is, let's say, x to the power 3 instead of x to the power 2. Now what will be dy by dx? Okay, just work it out and tell me.
8x square.
नहीं बेटा, x cube है ना अभी है. So what is differentiation of x cube?
3x square.
3x square. Na? So it will become 4 into 3x square.
12x square.
Yes. No, so we just have to apply this step by step. Na? So dy by dx, I'll replace y as what? I'll replace it as 4x cube. Now the moment I replace it as 4x cube from this thing given, I can see 4 is a constant. So next step I take 4 outside. I'm applying this property. So the constant is simplified by taking it outside, and then I apply this principle. That, sorry, not this one, this one. That differentiation of x to the power n is, so this becomes 4 into n x to the power n minus 1. So that is 3x square. So finally my answer becomes how much? 12x square. So dy by dx, which is differentiation in this case of 4x cube, is now given by the formula 12x square. ठीक है ना?
Sir, it will be 4 into 3x cube, right?
नहीं बेटा, x to the power n minus 1 होता है ना.
Yes, sir.
Differentiation of x to the power 3 is 3 into x to the power 3 minus 1. We've done this twice today, no?
Okay.
So you have to be very precise and careful. No? This is like doing algebra. Now, each and every term, each and every step is very important, no? When you're applying the differentiation formula. Anyhow, so we have seen like the most basic formula of differentiation today, which is the power rule or differentiation of x to the power n. And along with that, we have seen these two properties, that differentiation of a constant is 0 and differentiation of a constant multiplied by a function is equal to constant into differentiation of the function. Okay. So I will give you some practice questions based on this also. Plus I will send you the answer key and hints for the previous worksheet that I've sent. So you can go through those, but I'll be discussing that worksheet also in the next lecture. Okay.
So I will provide these notes, no?
Yes, I will provide these notes and the recording of today's lectures. Okay, so please make sure that you revise from the notes or the recording, whatever is preferable for you. And each of the numerical examples that we have done in class today, na, make sure that you revise it by doing it on pen and paper yourself once again. Okay. And if you have any doubt while revising, please note down that doubt and keep it ready in the next lecture so that we can start with the discussion of that doubt. Okay.
Okay, sir.
Okay, so that's it for today, students. Wish you all the best and thanks for attending.
Okay,
Thank you, sir. Have a nice
Thank you,
day.
sir.
Okay,
Thank
same to
Thank
you.
you,
Have a nice
sir.
day.
Bye.
Sir, you will post the assignment in the group, no?
Yes, I will post it in the group and it will also be posted on the website from now on, right?
Okay, sir.